Hi, welcome to the Calculus 2 lecture series. We are in the unit number 1. We talk about the applications of the integration. And this is our lecture number 3. We're going to talk about how to find the volumes and by using the cylindrical shell methods here. For the lecture number 2, we'll talk about the method how to find the volumes by using the disk or washer methods. And this is just a different technique. And so sometimes, depend on what your function looks like. Sometimes the disk and the washer method will be easier, and sometimes cylindrical shell methods will be easier. It just depends on whether it's easy to convert the function or not. So let's take a look at what is the cylindrical shell method. So let's go ahead, go to our lecture notes here. Okay, so the key concept we're going to cover in the lecture number 3. So basically is how to find the volumes here of the solid. Okay, also this is the revolution. That means I'm rotating the region along certain lines. Sometimes x-axis and sometimes y-axis, or sometimes it's just the line by using the shell methods here. Okay, so so what is the shell method? And I typically kind of like to use the example for apple. Of course, the apple is not like the perfect shape, but I think we can demonstrate what is the idea. So for apples here, right? So for apple here, for example, this is your apple, right? And you want to find, you want to find the volume of this apple. So what is the disk and shell? What is the disk and the washer method we did in the previous lecture? That's basically I'm cutting this apple this way. So I will get so many different slices, right? So each slice, if my apple is very round, will be a disc, right? So then I find the volume for each disc. Then I add them together. And in order to find the volume of the disc, we say pi r squared times the height. Correct. So that's how do we say it's the disk method. So we cut the apple in this way. So we can find the volume of this apple. Now, what is the shell method? I like to, so for the shell methods here, I don't know how to draw, but instead of you cutting the apple this way, so imagine yourself, you are using a peeler, right? So you peel the apple's skin. So you peel the apple's skin, very thin layers of the skin, the whole apple's skin, you peel that. Then you kind of expand that out. That will be what? That will be a rectangles, right? So you peel the first skin, after skin's out, then you peel the next level, then you peel the next level. So it's kind of like, you find the volumes, right? It's kind of like this way, kind of like this way for each one, right? So you kind of, the peeled off one layer, peel off the other layer. So when you peel out that layer, you kind of expand that. So what this, after you peel that, what is this one will be? Will be the rectangular. Right? And then if you cut the apple like this way, you will get a disc, right? So this will be a rectangular. And because you have the thickness, right? Because you have the thickness, so this will be a, what here? This will be a rectangular cylinder. All right, so that's why we say we're going to talk about using the cylindrical shells method. So it's kind of, you imagine that you peel that one peel and the next one and the next one. So it's a different way to cut your apples here. All right, so that's what we talk about the shell method. Like I said, if the problem give you say, hey, find the volume, you can use the disk method or the shell method. And sometimes, the disk method is just be very difficult to do, or, have more steps involved, and then you can use the shell method. Or sometimes, the disk method is easier than the shell methods here. So like I said here, right? So let's take a look at the shell methods here. Basically, it's kind of peeling. So you get a rectangular cylinders, right? So, okay, so let's take a look at what that means here, right? So let's do here, okay? So just like we did before, if I have a function here, all right? So this is my function, f of x. Let's say I'm going to rotating around the y-axis here. So just like we did before, so you kind of go like this, right? And so if this is the area, like we say, if this is the area I'm looking for, so that's the area, that's the region I'm going to rotating. Right, so this is the region I'm going to rotating here. And then when you get over here, you will get something like that, right? So if the same length here probably will be better. So here, right? So here, after you rotating, you are want to find the solid was generated by rotating this regions here. All right, so now we have the, so you say, okay, from what we learned before, we can use the, the washer or disk method. All right, that's fine. Let's see here. So if you cut the disk out here, right? So if you say you cut the disk out here, yeah, so you can use the, so then this will be the big disk, and then this will be the slow disk, right? So that will be your washers here. Okay, but then if you take a look at all the way it will work till here, but then if you go, let's see here, let me give a better color. Okay, so here, so how about now if you go to this region here, if you cut so this is your big disk, and then your small disk is here. So this will be your washer. So for the blue washers here, the outside, the radius is whatever is here, the inside is fixed also. But for the purple disk, right? So the outside is here, and the inside, the small one, is attached to this function. So like for this methods here, so for these functions here, if you like, of course, you can use the method we learned before, but then you need to divide it into two parts. You need to add them together, right? So that means you need to do the integration twice. All right. So, but you will get the same answer. That's why I said, okay, so if this is a, let's take a look at what is the shell method does. Okay, the shell methods here, remember, is peelings, right? So kind of like similar, like peeling the apples here. So if this is my f of x, okay, and if this is the area, the same thing, I want to rotate here, right? So this is the, okay, so this is the, so the same things here, right? So I am looking for the volume generator by here and here, right? But instead of cutting the disk, perpendicular to the y-axis, what I'm doing here, I say, let's peel that, right? So let's peel that. So basically you cut, so you have like this way, right? So in here, you have this way, see here, right? Okay, then like in here, you do like, so you rotate like this way. Okay, so I hope you can look like, so shear method is basically, then you look at this little layers of the shell, right? Or the skin of the apples here. So when you open up this purple ones here, what is going to show you? It's going to open up like a rectangular, right? And with a very, it's going to kind of will be rectangular, like you're going to have a rectangular like the prisms here, right? So it's kind of like when you open up, you will go like, just like we said, when you open up, when you touch it, right? So then I can find the volumes here. So what is the volume? The length of here will be what? Is the circumference of the circles, right? So it's going to be 2 pi what? 2 pi r's, right? So now what is the, what is the r's here? 2 pi r, right? So take a look. So here, the 2 pi r, so it's going to be from here when they touch here, right? So it will be what? Whatever is this x distance here. All right, so I know my circumference here will be 2 pi times my x here. So this is basically what is this one? This is the circumference, right? 2 pi r. Right, and now because I'm trying to find the volume of this rectangular prism, so what is the, what is this little thickness? That it will be my delta x. Now, what is the width here? What is here? Right, so this one's here. This is the one, the length times width, right? So this one's here will be what? This is the function f of x. So, right, because this is the height of that, so you say times f of x. So this will be what? This will be the, the one what? One volume of those shell, kind of like you peel the apple, that one peel, you will have some volume of like the apple you peel, right? So it's 2 pi r times f of x. And then the whole volumes here will just be by the Raymond Sum, you integrate, this is the AB, then the 2 pi r f of x dx. So if you, okay, so here, one thing we need to be very careful, right? So this example I give you here is I am rotating around the y, and because you do the shell methods here, it's different than what we do the disk. When the time we talk about the disk method, if you're rotating to the y, you're going to integrate to the y. So now this is kind of like the become the opposite. If you rotate into the y, you're going to integrate to the x. And the whole purpose here is, remember, like we talk about if I want to use the disk methods, right? One of the things, I need to change the x to a function of y. If I'm rotating to y, correct? Sometimes this function is very difficult to change to y. So maybe the disk method will not be easy, good one to do. So for example, if my f of x, let's just say it's like x squared plus 3x minus 5, something like that, right? So if my f of x is equal to x squared plus 3x minus 5, I'm rotating to the y. So I know, from the previous lecture, if I'm rotating to the y, I need to change it to the x equal to some type of the function of the y. And from here to here, what happens? Very difficult, right? So it's almost impossible, and without have a very complicated square roots, those things, right? And then after you do that, and then the integration probably will be other issues, right? So that's why we talk about the shell method. So shell method, basically you cut a thin slice, right? You cut a strip. Now, when you open that strip up, it's a rectangular, and then that will be a rectangular what? Rectangular prism, because you're going to have, it's kind of like a little box, you have a little bit of thickness here. All right, so now let's take a look at some examples here, right? Okay, so for these examples here, right? So now let's take a look. Let's say use the shell method. Just like we did before, it will be good, always graph it. All right. All right. So now here, let's take a look here. So for this one here. All right. So I want to graph it. So find the volume of the solid rotating to the y-axis region bounded by the y equal to square roots of x, y equal to 0, and x equal to 1 and 4. So, okay, let me use a different color. So this is y functions, right? So this is y equal to the square roots of x. And now y equal to 0 is the x-axis, x equal to 1, then y equal to 1, x equal to 4, right? So y equal to what? Y equal to 2. I'm going to rotating along the y-axis. Okay, so like always, we are try to find the volume generated by these regions here, right? So we're rotating along the y-axis here. Okay, so now, of course, for here, now let's take a look here, right? So what is the shell methods here? So let's say here, that means I'm going to, so here, let's color that out. So we know we want to find the volume generated by, oops, here, this is, okay. Here, so this is -1 to 4, all right? So we want to find the volume generated by here. Okay, so like I was saying, for these ones here, if I want to use wash method, I need to do it twice because from after they passing this point, then here, it will be like the two different, this will be like the cylinder, the cylinders here. So what I will do here, okay, let's do the shell methods, right? So the shell methods here, we say, okay, you cut a slice here. Let me get a different color. Okay, so you cut a thin slice, like I'm peeling the apples here, right? And now you want to rotating along the y-axis. Okay, so you're rotating here. Like I say, if you graph it, will be a lot easier to solve it. And then you are rotating, so like we say, always graph here. Oops. All right. All right, so you always graph like that. Okay. Okay, so basically I'm trying to find the volume of this thin layers of peel. Okay, see here? Okay, so that's the thin layer of the peel I'm trying to find. Okay, so now the first thing is here, I need to open this peel, right? So after that, I'm opening up. So I'm going to get a rectangular and with a little thickness. The thickness will be here, right? Little thickness. So what is the length of this rectangular? The length of this rectangular will be the 2 pi r, will be the circumference, correct? Okay, so here, this is the, okay, so here, this is the radius, right? So whatever the x is here, right? So this is the x value of my radius. So I know the circumference is 2 pi r, so it's 2 pi x, right? Okay, now let's take a look. The height of this little strip is here, right? So here, from here to here, right? This is the height. So what is this height? Yeah, this is a function. So y equal to the square roots of the x, right? So this will be what? The square roots of the x. All right, so make sure the color coding is here, right? Okay, so now I can just use the Raymond Sum concept. So I know the volumes will be the length times the height. So it's 2 pi x times the square roots of the x, right? So then in here, the little thickness we talk about is what? The little thickness here is will be what? Our dx here. So what is the x range? From the 1 to what? 1 to 4. Then this will be a pretty straightforward integration. So this will be 2 pi. So this is x to the 3/2 dx. So I assume everybody can know, or you can take the integration. This will be 124 pi over 5. Of course, like we say in here, if you want to use the wash method, you definitely can use it. It will give the same answer, but it will be way more complicated because you need to do the wash method twice. All right. So like we discussing here, you need to do the wash method, one above and one in, the below that, below these points here. All right, so that's why you need to do twice. And but the shell method for this problem is a lot easier. Okay, so now let's take a look here. Number 2, see here. So let's say they use the shell method to set up definite integrals for the volume of the solid and rotating along the x-axis. Here, I want to emphasize here, right? So in here, let's take a look here. So the shell methods here, this one, let's say, is rotating to the y-axis. Then it turns out what I'm integrating to the x. That's kind of opposite to the disk or washer method we learned before. All right, so now let's take a look at the second one, see here. So use the shell method to set a definite integrals for the volume of a solid. Okay, so x equal to the y square. All right, so in here, let's do the same thing. Always graph. That will be very, very helpful, right? All right, always graph here. And then in here, x equal to the y square. All right, so x equal to the y square. So this will be my functions, right? So this is x equal to the y square. And I'm going to what? I'm going to rotating around the x-axis here. And the area I want is 0 to 4. All right, so this is 0 to 4. Okay, so like we did before, we always highlight here. Right, so you can highlight here. Okay, I'm going to rotating these regions, right? Okay, so these regions, so when you're rotating here, you will get it like here. Right, rotating to the x-axis and in here. So these ones here, if you want to use our, the method we used before, the disk method, this will be a pretty simple one. Use the disk method because you can just cut it and then you will see it's a single disk here, right? So I'm finding here. Okay, but in here, the problem say, hey, let's try to practice the shell, right? Okay, so when we try to practice the shell methods here, right? So I'm rotating along the x-axis. So what I need to do, see here? Okay, here is what we do. You say, okay, let's cut I'm peeling, just like we peel the apple again. I'm peeling a thin layers, right? So this layer going to rotate into here. Right? Okay, and then in here you go like this. So always graph it, so we'll make the things a lot easier to visualize it. So did you see that? That will be a very thin layers of this volume you peeling off. So after you peeling off, this thin layer will become what? Become a rectangular. Okay, so now let's do the same thing. So what is the length of this rectangular? The length of this rectangular here will be from here to here, right? So it's a radius, right? So we'll go the radius, right? So will be the radius here. So it will be 2 pi. So whatever the distance here, we call this the y. right? So the length of here, when I open it up, so this is 2 pi r. Am I right? Okay, so now after that, I need to have the height. So that's why I always recommend, try to graph it, and then so what is my height of this rectangular sheet is here, from here to here, right? So this is the height of this cylindrical sheets here. So the heights here, so this is ended 4, this is ended x equal to the y squares, right? So what will be the height here? The height will be 4. Okay, so this will be what? This will be 4 from here, right? So this is 4 minus, right? So 4 minus y squared, because the height will be from this fixed line to hit this curve. It's 4 minus y squared. Cool? All right, now, of course, we have a thin, very, very thin height. That's how we can find the, very, very thin thickness here. So we can find the volume of this rectangular prism. Okay, so now the volume is here. So it's 2 pi, so length times width. So it's 2 pi y times 4 minus y squared, thin layer dy. The y is from what? X equal to 4, y is 2, right? So it's from 0 to what? 0 to 2. See here. You see here, this is the same thing because I'm going to rotating along the x-axis. If you use the disk method, then your integration is dx. But now I'm using the shell method. That's why I'm integrating to dy. Okay, so this is also a very simple. You can integration. You can move the 2 pi y out. So this would be the 4y minus y cubed dy. And now this is a pi. Okay, pretty straightforward, right? Okay, so remember the last lecture, we also talk about instead of rotating along the x-axis or y-axis, I can rotate along any lines here. The lines here is just a shift, to the x-axis or y-axis. So let's take a look here first. It said find the volume of the solid obtained by rotating the region bounded by this number and about the line x equal to 2. Okay, so the first things you see x equal to 2, really like we did from the previous lecture. So this is what? This is a shift of what? Really is y-axis, right? Because of the shell method, I know I'm going to integrate with respect to which variables here. Is going to respect to what? Because to x variables here. So sometimes this will help us to set up. All right. Okay, so now let's do that. All right. So the first things here, let's graph it. Like I said, we always love to graph. All right, so y equal to the x minus x squared. So when x equal to 0, y equal to 0. Okay, so it's here. When x equal to 1, y equal to 1. All right, so 1 is here. Okay, then this is my function. It's like some quadratic here. All right, so this is the area I'm going to rotating. Right, all right, so everything is good. So this is 1, this is 2, this is 3, this is 4, right? Okay, so now let's see here, because this is rotating along the x equal to 2, like we did before. Okay, so 2, so it's really just a shift of the y-axis, right? So this is x equal to 2. So this point, okay, this point is going to be boom, rotating to here. This point is going to boom, rotating to here. Correct? All right, so this will be our, right? And now I'm looking for the, the volume generated by rotating this yellow things here. Okay, so now we're doing the shell methods here. So that means I'm peeling off. All right, so let's do that. So that means the graph it, I'm peeling off here, get a peeling off here. All right, so because it's respect to the y, even if I say x equal to 2, really it's a shift of the y-axis, right? So this will be my little layer of the, the rectangular things, a little layer of the cylindrical cylinder. I'm peeling off here. So here. So far, so good. All right, so now after I peel off, I always recommend to do a picture. So here is your rectangular. All right, so now the peeling off here, this is the radius, right? So from here, this is the radius. So this is my x value, whatever the x value. So what is the radius here? Radius is what? Is 2 minus whatever the x is here, correct? So I know my length here, this is 2 pi. What is the radius? Radius is, if this is x, so this radius here is the 2 minus out this x value. So it's 2 pi r. So it's 2 minus x. So far, so good? All right. So now let's take a look. This is my height, right? So this is my height. So this is this part. Right, so this part, that is pretty good. That's just the function. So what is this one here? That's just the f of x function. So this is x minus x squared, right? See here, from here to touch these functions, right? So it's x minus x squared. Of course, like we said, it has a very thin thickness here, right? So that's why we get a kind of rectangular prism. Okay, so now I can find the volumes here. The volumes will be length times the width times the height. So it's a 2 pi 2 minus x times x minus x squared dx. Is match what we assume here, right? Dx is this. So this little thickness is delta x, right? So by the Raymond Sum, you just integrate will be dx. Okay, so what is the x region? So this is my original region. So it's what? From 0 to 1. So this one is also pretty straightforward integration. You can just get a 2 pi out and then this one, and you FOIL the remaining. Right, so you just FOIL out the remaining. So we can do a quick one. So this will be 2x minus 2x squared minus x squared plus x cubed, right? The dx, and then you will find that this answer is pi over 2 here. Right, so it's exactly the same thing like we did for the lecture number 2, draw a picture. So even let's say shift to a specific line, let's just shift off the y-axis or x-axis here. Okay, let's take a look at the last examples here. We have 2 parts for last example. So so we said the figure below, I have not drawn that yet. So it's bounded by the curve y equal to the x squared and y equal to the 2x and rotating about the line. Okay, so let's highlight here. We're rotating about the line x equal to -1. So remember, that means if I'm rotating to the x equal to 1, that means it's a shift of what? Shift of the y-axis, correct? The shift of the y-axis. Then my integration will be what? Respect to what? Respect to the x. So maybe this can help us to set it up. Okay, so the first thing is here, they said let's try to use the variable as the integration. So let's take a look at let's do the first graph first. Let's do the graph first. Okay, so this one's here, so y equal to the x squared. So this is 1, 2, 1, 2, 3, 4, something like that, all right? So, okay, so let's see here. So y equal to the 2x is this one, and then I have okay, so I have this is called something like this, right? So that's what is the area. I'm trying to rotating. All right. So this is y equal to the x squared. And this line is y equal to the 2x. I'm rotating along the x equal to the -1s here. All right, so now this is the 1, -1, this is -2, -3. Okay, so now let's do just like we did before. Okay, rotating respect to the -1. So drawing your new, drawing your new axis here. Okay, so now let's take a look at what is my rotating. This point going to where? Going to here, right? It's one distance from the new origin. And this point go over where? Go over here, right? Okay, so now my line, my graph going to rotate into here, like this way. It's not very good drawing, but okay, let me try again. So here, all right, so here, hopefully it looks prettier, okay, whatever. All right, so here, this is my, I get rid of my x-axis. All right, so this is the rotations here. So they said, hey, first things here, say, let's do, right? So let's do x variable as the integration. So I know this is the shift, right? So in order to get the x variable, I need to use the shell method. We say, okay, let's do the shell method. Okay, so let's do this. All right, so the shell methods right now. Okay, so let me cut a slice, cut a piece of this, like here, peeling a piece, right? So here, peeling a piece. That means you have here. So you have a thin, like the cylinder here. So this will be your cylinder, the little cylinder shell you're peeling off. All right, so like we said here, okay, let's try to put the things into the number. So first things here, right? So the radius is from here to here, whatever. When you reach here, it's the x here, right? So it's x here. So, but from here to here is x, but you move the line to the left. So what is the radius for here? So it's a 2 pi r, right? Supposed to be x, but you moved, so you add the radius is x plus 1. See here, this distance is x plus 1. Am I right? All right. So now after that, I need to find the the width of this one's here. So it's here. Hey, so look here. That will be the differences for this function and the green function. So the width for this rectangular will be the 2x minus x squared. Correct? All right. So now we have a little thickness here. This is my what? Delta x here. So now I can find the volume will just be by the Raymond Sum concept. It's length times width times height. So it's 2 pi x plus 1, 2x minus x squared. Then the delta x become dx. So what is my x value? My x value is from 0 to 2. And so this integration is super easy also. So you just take the 2 pi out and then 0 to 2, then you fold it. So it will be 2x squared minus x cubed plus 2x minus x squared, right? dx. And then you can get this will be the 16 pi over 3. Okay. All right. So now let's take a look. They said, how about the second part is very interesting. They say, hey, how about I want to take the y as the variable of the integration. Okay, so if you want to take the y as the variable as the integration, that means I would need to use the disk method, right, instead of the shell. So let's redraw this picture. So this is 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, and this is my new. All right, so here it's the same things here. So this is 1, 4, and this is the. Okay, so here this is the curve, and this is the curve. See here. All right. So now in here, this is the volume I want to do by, by rotating it. Okay, so now we say, okay, since I'm going to integrate to y, right? So that means I need to what? I need to have what here? I need to do a disk method or washer. So you say, okay, if I cut this way, that would be a pretty good disk, right? Okay, so after I do that, then I need to cut out the inside. So what is here? That will be my what? That will be my washers, right? So let's take a look for this washer methods here. What is my out radius? So what is the radius, the big one, out radius? So from our previous, we use R1. So what is the R1? R1 is from here all the way to where? To this green functions, right? So the R1, so this will be my R1 here. So from to the green functions, right? So this is y equal to the x squared. Right, so this is, I think that's the correct one, y equal to the x squares, right? So remember, when we try to do, so this is y equal to the x squared. But when I try to integrate to y, I need to change it to the function. So this function is not bad, so x equal to the square root of the y. Right, so this will be my radius. But in here, because you shift, so the outer radius will be 1 plus the square root of the y. Correct? Okay, now my inside radius. Okay, so this is my inside radius all the way to this functions, right? Okay, so my R2 see here. So what is my inside radius? This function is y equal to the 2x. So this one is easy to change also. So x equal to what? Y over 2, right? So this is the x equal to the y over 2. And now the same way, the radius will be 1 plus half of the y, right? So now I know I can use this. This is really the washer method. So it's instead of to find the circumference, I need to find the area. So the volume will be pi r squared. So pi r squared, so it's 1 plus the square root of the y to the square, right? Then minus the small disk inside, so it's a pi r squared again. So it's 1 minus y over square. Now I'm integrating to y here. Now what is the value of the y? From 0 to 4. And so this ones here also is just like the, the algebra foil. If, you can take the pi out, then this is 0 to 4. Then this will be 1 plus 2 square roots of the y plus y minus 1 plus y plus y squared over 2. Then dy, right? Then you can use a simple power rule to integrate this. And of course, you will get the same answers here. Okay, so this, like I said, for each one, you probably can use a disk method, or you can probably use a shell method. It depends on, sometimes one is easier than others, sometimes, one is more difficult than others here, right? So the shell method, remember the difference is just like we talked about in the beginning, is kind of the finding the volume of the apple, depends on which way you cut the apple, right? All right, so remember, right? So if you cut like we did in the beginning here, if you cut the apple this way, that's the disk method. If you peeling the apple one layer out at a time, one layer out at a time, then each peel you come out is rectangular, right? So it's a rectangular prism. So basically, then you can find the little volume of each peel. Right? All right, so that's it. That is how do we find the volume by the cylindrical shelves method. Like I said, the best way is graphing, right? So you graph it, and then you will not get confused. So where is your radius? Where is your outer radius? Where is your inner radius here? All right, that's it. And so from the first 3 lectures, we find how to find the volumes, right? By, if your volume generating by rotating a region, so we have a disk, a washer, and shell method. If your volumes is just some solid layer, you can do the slice methods, right? You slice it and then see what type of the shape is your cross section. All right, that's it. And so our next lecture, we're going to talk a little bit about the physics applications. All right, have a nice day. Nice talk to you later. All right, bye.